Hello everyone, this is Dr. K.Revathy. Here we are going to see about the heterocyclic compounds such as furan, pyrrole, thiophene, pyridine. Those preparation and properties we can see in this session. Here, first we should know what is an heterocyclic compound. It is a cyclic compound with one or more heteroatoms in that compound. The heteroatom means it may be a nitrogen or sulfur or oxygen. Here these are all the examples for 5-membered heterocyclic compounds. It is a pyrrole, 5-membered ring. Here one of the atom is nitrogen. Here, this is another example of nitrogen containing 5-membered heterocyclic compound. It is known as indole. It is also a 5-membered heterocyclic compound. We are having oxygen as a heteroatom. And this is thiophene. We are having sulfur as a heteroatom. And these are all the examples for 6-membered heterocyclic compound. This is a pyridine ring, which is similar to benzene. One of the carbon is replaced by an heteroatom nitrogen. It is quinoline. Similar to the structure of naphthalene, one carbon is replaced by the nitrogen heteroatom. This is isoquinoline. The difference between the quinoline and isoquinoline is the position of nitrogen. It's only the difference between the quinoline and isoquinoline. And these are all the examples for 6-membered heterocyclic compounds. First, let us see about the pyrrole and its structure and its properties also we can see in upcoming slides. This is the general structure of the pyrrole, 5-membered ring with nitrogen as an heteroatom. That is, this structure contains 4 carbon atoms. Along with that, 1 nitrogen atom is there. These orbitals get hybridized to give sp2 hybridized state orbitals, and these orbitals get overlapped with s orbital of hydrogen atom. It provides the formation of sigma bonds such as C-C, like this, the C-C sigma bond, C-N sigma bond, CH sigma bond, and NH sigma bond. Here, each atom of this pyrrole moiety is having an unhybridized p orbital. Still, there is an unhybridized p orbital which is found to be perpendicular to the sigma bonds. This unhybridized p orbital in all the atoms of the pyrrole, we are having an unhybridized p orbital which is found to be perpendicular to this sigma bond. Here, one carbon is having 1 electron. So totally 4 carbon atoms, we are having 4 electrons on 4 carbon atoms. And there is a lone pair of electrons on the nitrogen atom. So totally we are having 4 electron from carbon, 2 electron from nitrogen. So totally we are having 6 pi electrons. And the lateral overlap of these p orbitals of carbon and nitrogen produces the molecular orbital containing 6 pi electrons. And when coming to the aromatic nature, the pyrrole molecule obeys the Huckel's rule. That is, it obeys the 4n plus 2 pi electron rule, because it is having 4 pi electrons from the carbon-carbon double bond and 2 lone pair of 2 electrons, that is a lone pair of electrons on nitrogen atom. So totally it is a 6 pi electron. It obeys the Huckel's rule. The structure is found to be planar, cyclic. So the compound is said to be, and also there is a complete delocalization of pi electrons inside the ring. The lone pair of electrons is involving in the delocalization of pi electron. So this is regarding the structure of the pyrrole. Here we are going to see the preparation of pyrrole. Here we can synthesize pyrrole from two methods. By the reaction of furan with ammonia in presence of aluminum dioxide, at very high temperature, it provides pyrrole. The second reaction is the reaction of butane to butane diol reacts with ammonia on heated up at certain pressure, it produces pyrrole as a product. Here we are going to see the properties of pyrrole. This pyrrole was found to be more reactive than the benzene. Here, pyrrole also undergoes electrophilic substitution reaction because it is found to be aromatic in nature. Then, we have to find out at which position the electrophilic substitution reactions takes place, whether at second position or at the third position. At which position it provides the most stable electrophilic substituted compound we should find out. For that we should write down the resonating structures of two possible attacking positions at second position as well as at the third position also. When the electrophile attacks at the second position, it provides three resonating structures, whereas when the electrophile attacks at this third position, it provides only the two resonating structures. So while considering the structure of number of resonating structures, the attack at second position was found to be providing the more stable electrophilic substituted compound. So in general, pyrrole undergoes electrophilic substitution reaction at the second position, not at the third position. And the next point is acidic nature of pyrrole. Here, pyrrole is found to be a very weak acid because it contains NH. It reacts with an element potassium at a high temperature. It forms potassium salt, which on treatment with methyl chloride at a higher degree Celsius, it forms N-methyl pyrrole, which on further heating, it gives methyl substituted pyrrole. It indicates that the pyrrole is found to be very weak acid nature. Here we are going to see about the different electrophilic substitution reactions of pyrrole. We know that the electrophilic substitution reaction is in an aromatic compound, one of the hydrogen is replaced by an electrophile. That is, hydrogen is substituted by an electrophile. Here, already we discussed in the previous slide that electrophile will go to the second position. That is, in pyrrole, electrophilic substitution reaction takes place at the second position. So, while brominating the pyrrole, we will be getting 2-bromopyrrole. And on nitration, by using nitric acid in presence of acetic anhydride at very low temperature, it provides 2-nitropyrrole. Similarly, upon sulfonation by using SO3 as an electrophile, in presence of pyridine as a solvent, it provides 2-pyrrole sulfonic acid as a product. And on acylation by using acetic anhydride as an acylating agent, it gives 2-acetylpyrrole. Similarly, the pyrrole can undergo the diazotization reaction also to provide 2-phenylazopyrrole. And also the pyrrole undergoes the Riemann-Tiemann reaction with chloroform as well as the potassium hydroxide to form a formilated product such as 2-formylpyrrole. So likewise, as pyrrole is found to be an aromatic in nature, it undergoes electrophilic substitution reaction. Here we are going to see about the next heterocyclic compound, furan. The structure of furan was found to be similar to the structure of pyrrole. In pyrrole we had 4 carbon, 1 nitrogen. In furan, we are having 4 carbon and 1 oxygen. These orbitals get hybridized to form sp2 hybridized orbitals, and these sp2 hybridized orbitals get overlapped with the s orbital of hydrogen bond, provides the formation of sigma bonds such as Cc sigma bond. Here the Cc sigma bond, Co sigma bond, the Ch sigma bonds, etc. Here in oxygen, we are having 2 lone pair of electron. One lone pair of electron involves in the delocalization of the pi electrons. That is, already these 4 carbons are having 4 pi electron. Along with that, one lone pair of electron also involved in the delocalization of the pi electron, because all these orbitals are getting overlapped with each other to have a continuous delocalization. Because of that delocalization, it is obeying the Huckel's rule, 4n plus 2 pi electron system. So it is found to be, the furan is found to be aromatic in nature. When coming to the other set of a lone pair electron, it is found to be in the plane of the ring system. This lone pair of electron is found in the plane of this ring, and it is not involved in any delocalization. It is available for further reaction. Here, after the formation of sigma bonds, still each atom of furan is having an unhybridized p orbital which is found to be perpendicular to the sigma bonds, and all these p orbital of each carbon is having 1 electron, and oxygen is having 2 lone pair of electron, and 1 lone pair is already involved in delocalization of pi electron. The second pair is available, and all these 6 electrons getting overlapped to produce molecular orbitals. That is, the lateral overlap of these orbital provides a continuous delocalization of pi electron, found to be aromatic in nature. Cyclic planar delocalization of pi electron obeying Huckel's rule shows that the furan is found to be an aromatic in nature. Here we can see the preparation of furan. The furan can be prepared by pentose compound. On acidolysis at high temperature, it gives furfural as a product, which on treatment with zinc oxide or chromium oxide at high temperature, it involves the decarboxylation of furfural, provides the formation of furan. Here we are seeing the properties of furan. As we had seen the electrophilic substitution reaction of pyrrole, similarly furan also undergoes the electrophilic substitution reaction, because furan is also found to be an aromatic in nature. It also undergoes the electrophilic substitution reaction at the second position only. Upon bromination in presence of dioxin at low temperature, it provides 2 bromofuran. Similarly, on nitration by using nitric acid and acetic anhydride as a catalyst at low temperature 10 degrees Celsius, it provides 2 nitrofuran. Similarly, on sulfonation by using sulfur trioxide as an electrophile in presence of protein as a solvent at high temperature, it provides 2 furan sulfonic acid. And on acetylation by using acetic anhydride in presence of a Lewis acid BF3, it provides 2 acetyl furan. And the reduction of furan with ranitol provides tetrahydrofuran. This tetrahydrofuran can be used as a solvent for various organic conversions. Here we are going to see about the structure of thiophene. And the structure of thiophene is also found to be similar to pyrrole and furan. As we had seen already the structure of furan and pyrrole. Here in thiophene also we are having 4 carbon atoms and 1 sulfur atom. These orbitals get hybridized to form sp2 hybridized orbital, and these hybridized sp2 orbital overlap with the s orbitals of hydrogen atom, provides the formation of sigma bonds such as Cc sigma bond, Cs sigma bond, Ch sigma bonds. Here each atom of thiophene is still having an unhybridized p orbital, and the location of this p orbital is found to be perpendicular to the sigma bond. So p orbital of each carbon is having one electron, and sulfur is having two lone pair of electron. One lone pair of electron is involved in the lateral overlap of p orbital, provides the molecular orbital containing 6 pi electron, because 4 pi electron from the 4 carbon and 2 electron, that is a lone pair of electron from sulfur. So totally 6 pi electron involved in delocalization of pi electrons, resulting the structure of aromatic in nature, because it obeys the Huckel's rule, cyclic, planar in nature. And the remaining lone pair of electron is found to be in the plane of ring. It remains as such as a lone pair of electrons. Here we are going to see the preparation of thiophene. Here it is a disodium salt of succinic acid which on heating with the phosphorus salt, it provides the formation of thiophene. Similarly, it can also be prepared by the direct sulfonation of N-butane at very high temperature. It provides a cyclization of open chain butane to a cyclic thiophene. Similar to pyrrole, furan, thiophene will also undergo the electrophilic substitution reaction at the second position, and it is found to be more reactive than the normal benzene. Upon chlorination by using Cl2, it gives 2-chlorothiophene. Upon nitration with nitric acid, it provides 2-nitrothiophene. By the reaction of sulfuric acid, it gives 2-thiophene sulfonic acid. Upon acetylation using acetyl chloride, acetyl group was introduced at the second position. So, the electrophilic substitution reaction for thiophene, pyrrole and furan was found to be takes place at the second position of these heterocyclic compounds. Here we are going to see the desulfurization of thiophene. That is, the sulfur has to be removed from the ring by using ranonical at a high temperature. It provides N-butane open chain acyclic compound. Upon reduction by using sodium amalgam in ethanol, it provides tetrahydrothiophene, as similar to the case of furan. In furan, we had seen that furan is getting reduced to tetrahydrofuran, which can be used as a solvent for various organic conversions. Similarly, thiophene can also be reduced to tetrahydrothiophene. This tetrahydrothiophene also can be used as a solvent for various organic conversions. Now, let us see about the structure of pyridine. Here, the structure of pyridine, it contains, the structure is look like similar to benzene. One of the carbon is replaced by nitrogen with its lone pair of electron. Here we are having sp2-sp2 interaction, that is CC bond formation. We are having CH bond formation by sp2 hybridized orbital and CN bond formation by sp2-sp2 hybridized orbital. We are having a completely filled lone pair of electron in sp2 orbital. Here in total we are having 5 carbon atom, 1 nitrogen atom. These orbitals get hybridized to produce sp2 hybridized orbitals. 2 of these sp2 hybridized orbitals overlap with each other, provides the formation of CC and CN sigma bond. Look at here, CC sigma bond obtained from sp2-sp2 hybridization. Similarly, CN sigma bond has also been obtained by sp2-sp2 hybridization. And then again this sp2 hybridized orbital getting overlapped with S orbital of hydrogen atom provides the formation of this CH. This CH, all these CH bonds has been formed by the overlap of S orbital of hydrogen and sp2 hybridized orbital of 5 carbon and 1 nitrogen. So it provides the formation of CH sigma bond. Here The sp2 orbital on nitrogen atom is found to be completely filled. It is said to be a lone pair of electrons on the nitrogen atom. Here each atom of pyridine is still have an unhybridized p orbital which is found to be perpendicular to the sigma bond. This is known as sigma bond. Cn sigma bond. This is Cc sigma bond. To this sigma bond, all the atoms is having an unhybridized p orbital. The lateral overlap of these p orbital produces pi molecular orbital. It provides a ring-like structure which lies above the plane of the sigma bond and below the plane of the sigma bond, as in case of normal benzene-like structure. And when coming to the aromatic nature of this pyridine compound, the molecule is found to be a cyclic structure. It is found to be planar in nature. All these atoms is involving the lateral orbital overlap, resulting the formation of pi molecular orbital with a 6 pi electron. So it obeys the Huckel's rule 4n plus 2 pi electron. A pi electron cloud is lying above the plane as well as below the plane. So the compound is found to be aromatic in nature. The pi molecular orbital above the plane is shown here. Similarly, for the below the plane is also shown here. This pi orbital zone is obtained by the p orbital overlap, that is unhybridized p orbital overlapping of each other. And here the nitrogen is having still the lone pair of electron is getting retained. Let us see the preparation of pyridine. Here, 2 molecules of acrolein is heated in presence of ammonia to provide methyl substituted pyridine. From an acyclic compound, a cyclic methyl substituted pyridine is obtained, which on oxidation by using strong oxidizing agent like potassium dichromate in presence of an acid, the side chain is getting oxidized, that is the CH3 is getting converted into COH. This 3-carboxylic acid, pyridine 3-carboxylic acid on heating with the calcium oxide, the carbon dioxide molecule is getting evolved. So the resulting structure is our expected pyridine. This is one kind of preparation. Similarly, by the reaction of acetylene with ammonia with the CHO methoxy twice in presence of alumina is also producing pyridine as a product. So in these two methods we can prepare pyridine. Let us see the properties of pyridine. Here, pyridine was found to be basic in nature. So when the compound is basic, it gets easily react with an acid. So what happens when pyridine react with HCl? It forms a salt formation. Because of the presence of lone pair of electrons on the nitrogen atom, note the point, it doesn't involved in the delocalization of pi electrons. Okay, this lone pair of electron doesn't involve in the delocalization of pi electron. Because of that lone pair of electrons availability, it is able to react with the H plus to form new NH sigma bond. So from this we can say that the pyridine is found to be basic in nature. It reacts with acid very easily. And we have to know that pyridine was found to be more basic than pyrrole. We should know that pyridine is found to be more basic than pyrrole. Here we are comparing both pyridine as well as pyrrole, because both are nitrogen containing a heterocyclic compound. This is 6-membered heterocyclic and this is 5-membered heterocyclic atom. Both the molecule is having lone pair. Here nitrogen also we are having free lone pair of electron, but in case of pyrrole the lone pair of electron is getting involved in delocalization of pi electron. With this 2 lone pair of electron we are having totally 6 pi electron. Obeying the Huckel's rule, it gets involved in the delocalization of pi electron. This involvement of pi electron in delocalization it is found to be unavailable for further reaction of nitrogen. So it is found to be less basic. But this is not in case of nitrogen because it is having free lone pair of electron in sp2 orbital. Still it is found to be more free. Because of that lone pair of electron, it is found to be more basic. Let us discuss once again. In pyrrole, the lone pair of electrons in the nitrogen atom is involved in the delocalization of pi electron. That is, the lone pair of electron is not available for the formation of 2NH bond with a proton. But it is not in case of pyridine because of its easily availability of lone pair of electron for further reaction with the acid compound. It can able to form new NH bond with the protons. And here we are going to see about that pyridine is found to be less basic than the aliphatic amine. In previous slide we had seen that pyridine basicity with pyrrole. Here we are going to see the basic nature of pyridine by comparing with the aliphatic amine. Here both pyridine as well as aliphatic amines are having nitrogen as an heteroatom. Both are having the lone pair of electron. Both are having free lone pair of electron. Then how we can find out that pyridine is found to be less basic than the aliphatic amine? Here we have to be very conscious about the hybridization of lone pair of electron presenting in the orbital. Here in pyridine, the lone pair of electron are present in the sp2 hybridized orbital. But in case of aliphatic amine, the lone pair of electrons are present in sp3 hybridized orbital. Here when comparing the size of these sp2 and sp3 orbital, the sp2 orbital is found to be smaller than the sp3 orbitals because in sp2 we are having more s character. So when by comparing these hybridized orbital of sp2 and sp3 of lone pair of electron, we can find that the pyridine is found to be less basic in nature and aliphatic amines are found to be more basic in nature. Because in pyridine, lone pair of electrons in nitrogen is closely associated with the molecule because of its smaller in size and it is less available for the formation of bond with the proton. Already we had seen that it can easily react with the proton. But that reaction of proton is also not that much easily available because of the presence of lone pair of electron which is very close to the benzene, this 6-membered ring, and it is availability for further reaction with the proton is found to be less. So the basicity of pyridine was getting reduced. So the pyridine was concluded that it is found to be less basic than the aliphatic amines. Let us come to the electrophilic substitution reaction of pyridine. Here, as in case of pyrrole, thiophene and furan, pyridine can also undergo the electrophilic substitution reaction at either at 2 position or at 3 position. We have to find out at which position provides a stable compound, stable electrophilic substitution product as a compound. So when coming to the attack at second position, we are having only the 2 resonating intermediate structures. But when the electrophile attacks at the third position, we are having 3 resonating intermediate structures. So the electrophilic attack at the position of 3 is found to be more stable. So the formation of 3, that is third position substitution at third position was found to be more stable than the second position substituent. Let us see the electrophilic substitution reactions of pyridine. Upon nitration with the potassium nitrate and sulfuric acid at a higher temperature of 300 degrees Celsius, it provides nitro substituent at third position. That is, 3-nitropyridine is formed. Upon sulfonation by using fuming sulfuric acid at 250 degrees Celsius, sulfonic acid group was introduced at third position. Similarly, on bromination at a high temperature, bromine was introduced at third position to provide 3-bromopyridine. Here, we have to see the nucleophilic substitution reactions also for pyridine because Just now we had seen that pyridine undergoes the electrophilic substitution reaction also, but pyridine can also able to undergo the nucleophilic substitution reaction also. At the second position, we have to find out at which position the nucleophile gets substituted, either at second position or at third position. In case of electrophilic substitution, we had seen that at second position we are having 3 resonating structure, at third position we are having 2 resonating structure. But in case of nucleophilic substitution, either the position may be 2 or 3. We are having 3 resonating structures. But while studying the resonating structures, the attack at second position will lead to the more stable resonating structures. Attack at third position will lead to the less stable resonating structures. So, we can conclude that the nucleophile gets substituted at the second position of the pyridine. These are all the examples for nucleophilic substitution reaction of pyridine. First example is the reaction of sodamide at high temperature to provide 2-aminopyridine. Phenyl lithium at 100 degrees Celsius to give 2-phenyl lithium. In presence of sodium ethanol reduction, it gives piperidine. Similarly, on reduction with the hydrogen and nickel, it provides piperidine. So as of now, we had seen what are heterocyclic compounds, what are heteroatoms. In the heterocyclic compound, we had seen the structure, preparation and properties of furan, pyrrole, thiophene and pyridine. In case of pyridine, we had seen, in addition to the electrophilic substitution, we had seen the nucleophilic substitution reactions also. Then, thank you. Do you have any questions?